We are recording. Example 7. Use both long division and synthetic division to find all the zeros. Well, you know what? I'm gonna go ahead and say no to the long division. I'm gonna put my foot down, and I'm gonna put my other foot down, and now I'm standing on my own 2 feet, and I'm gonna say at the top of my voice, no to long division. You know why? Because we've already been there, done that. I wanted you to appreciate synthetic division, but I think most of y'all appreciate synthetic division compared to its long division counterpart, right? So let's go ahead and just do synthetic division. All right, now it says to find all the zeros. What's the degree of this polynomial h of x? 3. So how many zeros are we supposed to come up with at the end? 3, right? There's 3 of them. Because it's a cubic, though, if I know just one root or one factor, I can get it down to the quadratic. And of course, once I get it down to a quadratic, I'm home free. So really, to start with, I only need one root. Now, does this thing have an x factor in all the terms, like the previous example? It has an x factor in all the terms? No. If it did, I would know right away that 0 is a factor. That's an easy way to spot if 0 is a factor, if all your terms have an x in it. But they don't. So 0 is actually not a factor. If you plug in a 0 here, h of 0, you get 18. So it's not a factor. So I need to know one root so I can synthetically divide. Oh, it tells me x plus 1 is a factor. So if x plus 1 is a factor, then what's the corresponding root? X equals -1. Okay, so let's go ahead and do the synthetic division. Is h of x written in standard form? Standard form, remember, means descending order of degree. It is, right? So I need to write my coefficients down, and I always have a placeholder if anything's missing, but it doesn't look like anything's missing here. So I have a 3x cubed, a -12x squared, a 3x to the first, and an 18. And we leave a reasonable amount of space in between them, right? Bless you. Now we draw a line underneath there with the little box out front, and this box at the back should be what at the end here? It should be 0 if what they told us was true. If x plus 1 is actually a factor and -1's a root. Now what goes in the box in the front? 1 or -1? -1. Good. We always synthetically divide with the root. Now we bring down the 3 and we multiply and we get -3, and we add, we get -15. And then we multiply and we get 15. We add, we get 18. We multiply and we get -18. And we get 0. Lo and behold, we get 0. Yes, yes. Now this right here is the distilled product. These are the coefficients of the quotient. And what's the degree of the quotient? If it started off as an x cubed, it's an x squared. So it's degree 2. So what I'm going to do is I'm just going to focus on that. So I'm going to say, okay, what we have left is 3x squared minus 15x plus 18. And I want to find the remaining zeros. So I'm going to set that quotient equal to 0 and start over like it's a brand new problem. Okay, now because it's a quadratic, I can go straight to the quadratic formula, right? But we always try to factor first. And what's the first rule of factoring? Common factor. Do we have a common factor? 3, not a 3x, just a 3, right? So that leaves me x squared minus 5x plus 6. And that's going to make it real easy to factor the rest of it. So I can double bubble what's left here. And because it's a 1x squared, it's got to be an x and an x. And now I'm just looking for factors of +6 that add up to -5. Is it the old 6-1 combo or is it the 3-2 combo? It's got to be the 3-2 combo because the sum is negative and the product is positive. So they both have to be negative. And if you did the 6-1 combo, you can't subtract to get 5. So you have to add to get 5, and that's your 3-2 combo. Now using the factor theorem or the root theorem, if x minus 3 is the factor, what's the corresponding root? 3. And if x minus 2 is the factor, what's the root? 2. And let's bring down the other root from up above. What was the first root? -1. There is the solution right there. Those are your 3 x-intercepts. Okay? We found all the zeros. Now we could do one more than that. Now that we have the 3 zeros, they're all multiplicity what? They're all multiplicity 1. So they're all, they're all crosses. So I can go over here to -1. There's 2. And then here's 3 right here. So it's that. And does it come in the bottom or does it come in the top? It comes in the top? I asked kind of a loaded question. Yeah. The 3 in the front is positive. So that tells us that it exits the what? It exits the top. Yeah, I asked where it enters. because it's the right end behavior, right? So it exits the top. Now, because it's an odd degree, it comes in the bottom, right? It enters the bottom. Because it's an odd degree, it's opposite. So it's going to come in the bottom. It's going to cross. Let's see. I'm going to do it a little bit different. I'm going to have it a little bit steeper here. And then it's going to do this. And it's going to do that. Now, without calculus or a calculator, again, remember, we can't find the local max or the local min. We can't find the local max or the local min. But we could sure find the domain. What's the domain? That's easy. We could do that without any effort. Domain of H is all real numbers. Now, what's the range? All real numbers. Do we need the graph for that? Or could we have gotten that just by looking at the equation? We could have got it by looking at the equation. Why, Brady? It's an odd what? It's not odd. Odd means origin symmetrical. It's odd degree. Right. Let's remind ourselves that this is not an odd function. The graph that we drew does not have origin symmetry, but it is an odd degree function. Okay? All right. That wasn't too bad, right? That was almost Finizi. In fact, I think that was Finizi. I think we accomplished Finizi on that one. Any comments or questions? Today is barbecue dads and soccer moms. Tomorrow is Halloween. Oh, that's wide open, right? Tomorrow is Halloween dress-up day. Anyone going to dress up? Some of y'all look like y'all dressed up like scary monsters today. But I think that's just your normal face. Ooh, I got y'all. I got y'all, right? That's a burn. No. Okay, let's look at example 8. If f of x is 9x cubed plus 15x squared minus 77 minus 147, list all the distinct possible rational roots, and then find the remaining roots given that 3x plus 7 is a factor. Sketch the graph. Okay, so we crescendoed really, really quickly from example 7 to example 8, didn't we? My goodness. This is a cubic polynomial, so it can have up to 3 solutions. Is there any common factor, first of all, in f of x that we could factor out? It would make everything else easy. A 3? Well, the 9 has a factor of 3. The 15 has a factor of 3. Is 77 divisible by 3? Do y'all know the trick to determine quickly if something's divisible by 3? If the digital index of a number is divisible by 3, then the number is divisible by 3. What the heck is the digital index of a number? The digital index of a number, this is you don't have to know this, but it's kind of cool. The digital index of a number is the sum of all the digits. What's 7 plus 7? 14. Okay, now that's a 2-digit number. So you got 7 plus 7, that's 14. That's a 2-digit number, so now what's 1 plus 4? You keep adding the digits until you get a single 1-digit number. You keep adding all the digits until you get a single 1-digit number. That's 5. If the digital index is divisible by 3, then so is the original number. Is 5 divisible by 3? No, you could have done it with the 14 as well. Is 14 divisible by 3? No, okay. What about 147? Let's just figure out what's the digital index of 147. Yeah, good, because 1 plus 4 plus 7 is 12, and then 1 plus 2 is 3. So is 3 divisible by 3? Yeah, so what's the only number that is not divisible by 3? 77. He ruins it. If had he been divisible by 3, we would have factored out a 3 to begin with because it makes everything else so much easier. But alas, he's not. Okay, so we got to list all the distinct possible rational roots. So here we go. We're going to have the negative 147 up here, and we're going to have the 9 down here. These are the P's, these are the Q's, and now we got to list all of the factors. Are you ready? Are you ready for it? Any Swifties out there? How about plus or minus 1, plus or minus 147? Would you agree that those are factors of 147? Yeah, God, what about 2? Does 2 go into 147? No, how about 3? Yeah, plus or minus 3, and what's the quotient? What's the other factor? 3 goes into 14 4 times, that's 12 with 2 left over, and then 3 goes into 27. Not 49. So now that I know that it's 49, I know 4 doesn't go in, I know 5 doesn't go in, I know 6 doesn't go in, but does 7 go in? Yeah, so it's plus or minus 7, and what's the quotient when we go into, what's 147 divided by 7? 21. Good, 21. Okay, oops, let me put plus or minus 21. Is that all of them? That has to be all of them, right? Yeah, that has to be all of them. Okay, let's look at Q. This is a little bit easier. Factors of 9, plus or minus 1, plus or minus 9, and plus or minus what? 3. Okay, are you ready for it? You ready to list them? I am too. So here we go. P over Q. Here are the distinct possible rational roots. The way I do it is this. I start with the 1 in the bottom, and I distribute it to all of these other factors, like that. Now, anything over 1 is itself. Yes, yes? So I can just say it's plus or minus 1, plus or minus 147, plus or minus 3, plus or minus 49, plus or minus 7, plus or minus 21. Right? Now I go down to the 9. I do the same thing, but I do it with the 9. So all of these are over 9. And what do we end up with? We end up with plus or minus 1/9, plus or minus, does 140, is 147 divided by 9, does that simplify?
Oh, yeah. Oh, by 3.
How many times does 9 go into 147? 9 goes into 14 one time, with how many left over? 5? And then 57, does 9 go into 57? No, so that doesn't simplify. Okay. What about plus or minus 3/9? Does plus or minus 3/9 simplify? Yeah, so plus or minus what? 1/3. I'm going to simplify as I go if you're okay with that. Is it? Oh, we can simplify. We can divide both by 3. Yeah. Let me not simplify on this row. Okay, because I said I was going to do it and I didn't do it uniformly. So let's just write it 3 over 9, and then it's plus or minus 49 over 9. We'll just do it like this. Thank you. Plus or minus 7 over 9. I like your method better. Plus or minus 21 over 9. Okay. Ooh, that's getting to be a long list, isn't it? Should I keep going from left to right? Yeah, why the heck not? Now let's do the last one. The last one is going to be all of them over what? 3. So we get plus or minus 1/3, plus or minus 147 thirds, plus or minus 3/3, plus or minus 49 thirds, sorry, plus or minus 7 thirds, sorry, and then plus or minus 21 thirds, sorry. Why do I keep saying turds? It's kind of a fun word to say. Like when teenagers are like doing malicious things, old boomers say, "You little turds," right? You turds, right? That means poop log. Guess what we get to do now? We get to go through and simplify, and if anything simplifies down to something that's already listed, we don't have to list it again, okay? So here we go. Plus or minus 1, that's good, right? I'm going to cross them out as I go. Plus or minus 147. In fact, I can list all these again. Plus or minus 3, plus or minus 49, plus or minus 7, plus or minus 21. Okay, now we get into the fractions. Plus or minus 1/9 looks good. Plus or minus, and if I simplify this, how many times does 3 go into 147? 3 goes into 14 4 times with 2 left over, so that's 49 over 3, 49 thirds. Everyone agree? Okay. And then plus or minus 3/9, that's plus or minus 1/3. Plus or minus 49/9, does that simplify? 49 is 7 squared, remember? 7 is a prime number. So there, it doesn't simplify. So that's it looks like it should, right? And then plus or minus 7/9, we don't have that one yet. Plus or minus 21/9, that simplifies down to what? 7 thirds. Do we have that one listed yet? 7 thirds? I don't see 7 thirds anywhere. So I have to write it down. It wasn't listed yet. All right, now we're going to get some doubles, I believe, here. Plus or minus 1/3. Do we have that one already? Yeah, plus or minus 147 thirds. What is one? How many times does 3 go into 47? We already said 49 times. Do we have 49 listed already? Yep. So we don't need that. 3/3. Isn't that 1? We already have that. What about 49 thirds? Do we already have that? Yeah. What about 7 thirds? Sorry. We already have that. What about 21 thirds? That's 7. We already have that. So we didn't need any of those last ones. So now here's a great multiple choice question on the test. How many distinct possible rational roots. Count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24.
What was 21 there?
21 thirds? Yeah, that's 7. So we already had 7 listed. Yeah. So here's the good news. If we were interested in finding the rational roots, if they existed, remember the theorem doesn't guarantee they exist, but if we were looking for rational roots, we only have 24 things to try out using synthetic division. Now imagine you're back as a lonely teenager with no trick or treat on Unicorn Street to attend on a given Halloween evening, which is tonight, and you were just no calculator and you were left to find the roots of this cubic. You would probably rejoice at having 24 synthetic division processes to do, right? You'd be like, wow, that's 24 times the fun, right? I know how fun it is just to do it once. Imagine, like, we had fun right here, did we not? Imagine having to do it 24 times, right? Now, the good news is that 24 is a small number compared to if you were just trying out random values off the real number line, which would be infinitely many. Would you agree? That's a really lonely person that looks forward to trying out infinitely many, right? Tomorrow is a new day. But we only have 24 to try out. Now, you're always going to have a hint. So I said we can use the calculator to help us find the roots if we graphed it, but we don't need the calculator because it gave us a hint, didn't it? And in fact, it gave us one of the roots implicitly because it said 3x plus 7 is a factor. So let's write that down. If 3x plus 7 is a factor, comma, what is the root? X equals what? Not 7 thirds. Negative 7 thirds is a root. Is negative 7 thirds in our candidate list? It sure is. He's right there. Okay? Negative 7 thirds is in our candidate list. Now, the other two roots, once we get down to a quadratic, we can find by either factoring or using the quadratic formula. Okay? All right. Let's go ahead and do the synthetic division. I'm going to come over here to the far right side. Is it? Why did it do that?
Series.
Oh, it's playing No Roots by Alice Merton. No Roots. Nice. Way to try and get involved in the math lesson there, Spotify. I did not ask you to do that. No Roots. This one actually has 3 roots, Spotify, you stupid app. All right, let's go ahead and write down our coefficients. We got 9, 15, negative 77, and negative 147. 3, 2, 1, 0. Okay, so no placeholders needed. We draw our line in the box. What are we going to put in the box? Negative 7 thirds. And what should be in the last box? The remainder should be 0. Okay, let's give it a go. Bring down the 9. We multiply. Should we do 9 times 7 first and then divide by 3? Say no. We should divide first and then multiply. Go small before you go big. Remember we had that discussion earlier in the year. So what's 9 divided by 3? 3. What's 3 times negative 7? Negative 21. We slide that up into the next row. Now we add. What's 15 minus 21? Negative 6. Now let's divide. What's 6 divided by 3? 2. What's negative 2 times negative 7? Positive 14. Positive 14. Positive 14. Now we add vertically and we get negative 63. Yeah. Negative 7 thirds times negative 6 over 1. This divides out to give us negative 2. And now negative 7 times negative 2 is negative 14. Or positive 14. Oops. Got it? Okay, good. Roger that. Over. All right, now 63 divided by 3. What's 63 divided by 3? 21. What's 21 times 7? 147. Seguro. Orale. Let's add those together and we get 0. We knew that. Okay, now, what are we staring at down here? These are the what's of the who. The coefficients of the quadratic quotient, right? So, as we did on the problem above, let's go ahead and say now we're left with 9x squared minus 6x minus 63. And we want that to equal 0. So now we can just focus on a quadratic instead of a cubic. So we reset all of our mental flow chart and we ask ourselves again, now that it's a quadratic and it's equal to 0, we look to factor it. What again is the first rule of factoring? Greatest common factor. Do these three guys have a common factor as a number?
Yes.
What is it? 3. Let me factor the 3 out, and that gives me 3x squared minus 2x minus 21. All right, now I can focus on the inside. I'm not sure if it's going to factor, but you know what? I sure as heck am going to try. I sure as heck am going to try. I know 3x squared, 3 is prime, so it's got to be a 3x and a 1x. Now, with the 21, I have some options. It can be 21 and 1 or 1 and 21. Do you think those are going to work? I'm trying to get a 2 on the inside. So I'm trying to make my inside and outside products as close to each other as I can. If I use the extreme numbers like 1 and 21, I'm going to get numbers that are way too big and far apart from each other. So it's probably going to be a 7-3 combo, yes? Now, if I go with the 7-3 combo like this, that's probably not going to work because now I have a 21 again on the outside, don't I? And a 3x on the inside. That's not going to work. So what if instead of the old 3-7 combo, what if I did the 7-3 combo? That gives me a 7 on the inside and a 9 on the outside. What's the difference between 7 and 9? Los dos. Is that what we want? Yeah. Now, because the sum is negative, which number has to be negative, the 3 or the 7? You would think the 7 because it's bigger, but we're looking at the products. 7x or 3x times 3, which is 9x. The 9 has to be negative, yes? So in order to get the 9 to be negative, I need to make the 3 negative and the 7 positive. You're unfoiling this, first out or inner last. So it's a little bit of guessing and checking, but y'all can handle it. Now I can rattle off the roots. If 3x plus 7 is the root, what's the corresponding factor? Negative 7/3. Hey, didn't we already see him? So what multiplicity is he? He's multiplicity 2. What is going to happen on the graph there? Boing. Very good. A bounce. And what's the other root? 3. And he's in multiplicity 1. Did we find all the roots or should we keep looking?
That's all the roots.
That's all the roots. The sum of the multiplicities should be the degree. 2 plus 1 is 3. We found them. There's only 2 distinct real roots. One's a bounce and one is not cross. Okay, now it says to sketch the graph. So let's do it. Here's 3 right here. There's a root. And negative 7/3 is approximately what? Is it like negative 10 point something? Negative 2 point something. So we'll just call this negative 7/3. Are you okay with that? All right, now I'll pick purple. No, I'll pick green. I need to know which way I'm coming in. The leading coefficient is positive, so the right-hand behavior is what? What's the limit as x goes to infinity of f of x? Infinity. Therefore, what should be the limit as x goes to negative infinity of f of x? Seeing that it's an odd degree, it should be the opposite, negative infinity. So it comes in from the bottom. All right, so let's do that. It comes in from the bottom like this, and it bounces right there, boing, and then somewhere it turns around and it comes back up and it looks like that, and now we'll label it as f of x. Look how beautiful that graph is. Only the essential qualities are shown. Now, there is one thing that we would still desire, and that's the local minimum, but we can't do that unless we have a calculator or we know calculus. We do know the max. Let's go ahead and state that. I will always use a highlighter. Gosh, dang it. F of x has a local max of y equals what? 0 at x equals what? Negative 7/3. Yeah. What's the domain of this function? All real numbers. What's the range of this function? All real numbers. Yeah. Good. How many total local or relative extrema does it have? 2. A local max and a local min. Okay, good. Is it an odd function?
No.
Does it have origin symmetry? No. Is it an odd degree function? Yes. Yes. Now, let's look at this last thing right here. That last root that we found was 3. Was 3 also in our candidate list at some point? Yeah, there he is. So there you go. All of our roots ended up being rational. Remember, there was no guarantee that they were going to be rational. All of them ended up being rational, and they were all in the candidate list. So that rational root theorem really, really works. Is it a rational root that you found? You're asking, what if we find a root that's not in our candidate list? My question is, did you happen to find a rational root? Well, then you did your list wrong. Okay. Yeah. If you find a rational root, that is, if you find a root that's an integer or a fraction, and it's not in your candidate list, then you have an incomplete candidate list. You didn't maybe consider all the factors. Like 147, there's a lot of factors to consider. Maybe 13 is a factor of 147 and we didn't realize it or something like that. Okay. That means that you have an incomplete candidate list. Now, if you find an irrational root, like the square root of 2 or the square root of 5 or the square root of 7, that's possible. Those don't have to appear in the rational root theorem list. Okay. Do you have to what? Yeah, because it asked you to. It says to list all the distinct possible rational roots. We want to prepare ourselves. Remember, we're at some point leaving the footsteps of our founding forefathers who didn't have technology. Okay, but we want to appreciate what they had to do because these theorems are very important. So we're gonna go ahead and make the candidate list, which is only 24 numbers, but we're gonna stop short of having to try all those out blindly. Does that make sense? I wouldn't spend the whole period just putting y'all into groups and having you divide and conquer. All right, y'all try the first four, y'all try the next four, you try the next four, the next four, the next four, and synthetically divide and see if they work. One group is going to be successful when they divide through by 3 and it works. One group is going to be successful when they divide by 7/3 and it works. I'm not going to do that, but that's what they had to do back in the day if they were looking for these lists. I'm either going to let you use the calculator to tip you off as to which ones are which, or I'm going to give you enough information so that you can get it down to a quadratic, because once you get it to a quadratic, you can either factor it or use the quadratic formula. And all the ones so far we've been able to use the factoring method on, right? Right. Does that answer your question, Brady? Okay. Let's go ahead and go to example 9. Find all the real zeros of this 4th degree polynomial. List all the distinct possible rational roots. Use synthetic division to test. Okay. So this one is actually making us do what those lonely teenagers of yore had to do. Let's go ahead and list them. So our it's written in standard form. Our constant is 8. Our leading coefficient is 2. So these are the p-values. These are the q-values. What are the factors of 8? Plus or minus 1, plus or minus 8. I just work up from the low one, and I always put their mating factor. So after 1, I try 2. Is 2 a factor of 8? Yeah. Plus or minus 2, plus or minus 4. How about 3? Nope. How about 4? Well, I already got 4. So those must be all of them. Yes, yes? All right, for Q, the number is 2. It should be plus or minus 1 and plus or minus 2. So now I can list the ratios P over Q. There's not that many of them this time. It's plus or minus 1 over 1, plus or minus 8 over 1, plus or minus 2 over 1, plus or minus 4 over 1. And then I got all of them over 2. I think we can simplify as we go if we need to, right? Plus or minus 1 over 2, that's a half. Do we need plus or minus 8 over 2? No, because that's 4. What about plus or minus 2 over 2? No, that's 1. What about plus or minus 4 over 2? No, that's 2. So the only one that was novel or unique from that second iteration was the 1/2. So how many do we have? 1, 2, 3, 4, 5 times 2. We have 10 possible rational roots. Now, once it lists them, it says to use synthetic division to test your possible rational roots. I'm interested in finding 4 roots because it's a 4th degree polynomial, but how many do I really need to find before I'm home free? 2. Very good. Because if I can find 2, I can synthetically divide it down and get my quadratic. And once I have my quadratic, instead of doing trial and error with these rational possibilities, I can just factor or use the quadratic formula. So we just need to find 2. Let's find 2. So we're going to have to do trial and error. So let's go ahead and set up like a semi-permanent structure here. 2x to the 4th, negative 7x cubed, negative 8, 14, and 8. All right, who's going to be first in the hot box here? Who are we going to try out first? 1? All right, let's try out a 1. Bring down the 2, and you're going to get 2. That's negative 5. That's negative 5. That's negative 13. That's negative 13. That's 1. That's 1. That's 9. Is 9 0? No. But guess what f of 1 is? 9. Yeah. That's synthetic substitution. Okay. So I'm going to make a list over here of ones that don't work. Okay. These are not roots. Let's make a list here. Not roots. 1. So we know we used it. All right. What do you want to try next? Get rid of this. You have your little eraser. So you can just kind of slide it through there. You want to try negative 1? Let's try negative 1. The 2 still comes down. So we get negative 2. That gives us negative 9. That gives us 9. That gives us 1. That gives us negative 1. 14 minus 1 is 13. That gives us negative 13. And that gives us negative 5. Is negative 1 a root? No. But guess what f of negative 1 is? Negative 5. There's an ordered pair on the graph called negative 1 comma negative 5. But negative 1 is not a root. Okay, so we've tried out the easy ones first, and that's smart. Those are the ones I would have actually tried first. You want to just keep going? Try the next easy one, like 2? You want to try a 2? Let's try a 2. Let's see a 2. Okay, so there's a 2. I bring down the 2. I get 4, negative 3, bless you, negative 6, negative 14, and then I get, negative 28. And then I get negative 14, and then I get negative 28 again, and I get negative 20. Shoot. Doggone it. 2 is not a root. But guess what f of 2 is? Negative 20. Yeah. There's a point on the graph called 2 comma negative 20. All right. See how much fun this is? This is what lonely teenagers did on Friday night when the phone didn't ring. What should we try next? Negative 2. Let's try it. Negative 2. All right, so I bring down the 2. I multiply, and I get negative 4. Oh, I can already tell this one's not going to work. Can't you? Or no? Can we tell yet? Maybe. I don't think so. Let's keep going. We get negative 11. Then we get positive 22. 22 minus 8 is 14. 14 times negative 2 is negative 28. That gives us negative 14. And then we get positive 28, which gives us positive 36. Uh-oh. That doesn't work, does it? So negative 2 also doesn't work. I already wrote it in the not a root list. I guess I had an intuition about it. You want to try the fraction? Oh, man. You're brave. All right, let's try 1/2. Bring down the 2. What's half of 2? 1. You add, you get negative 6. What's half of negative 6? Negative 3. You add, you get negative 11. What's half of negative 11? Shucks. Negative 11 halves. Is it going to work now? No, if you're not reconciling your factors all the way to whole numbers, it's not going to work. So 1/2 is not going to work. 1/2 is not in there. Okay, so you don't have to complete it if you know it's not going to work. You want to try negative 1/2? All right, bring down the 2. What's half of negative 2? Negative 1. Then we get negative 8. What's half of negative 8? Positive 4, right? Because of the negative over negative. And then we get negative 4. What's negative 4 times negative 1/2? Positive 2, we add, we get 16. What's half of 16?
Yes,
We get negative 8, we get what? 0. Yeah! Woohoo!
Yeah.
We found a root. Okay? So I'm going to come over here and I'm going to say these are the roots. We get x equals negative 1/2. All right, now here's the thing. Since we've got it down from a x to the 4th down to now an x equals 3, we can set up a new semi-permanent structure here, which will always have one less iteration to go through, right? Because any remaining factor of the f of x is going to be a remaining factor of this cubic polynomial that we have right here. 2x cubed minus 8x squared minus 4x plus 16. Okay, good. So we've exhausted the fractions. So we've exhausted the 1s, the 2s, and the 1/2s. What's left to try? You want to go with a negative 4? Woo-wee! I like that. Lead with the negative. All right, let's bring down the 2. That gives us negative 8, negative 16, positive 64, positive 60, negative 240. Is that going to work? That's getting out of hand. Okay, we know negative 4 doesn't work, so I'll put him in the not a candidate list. It was worth the shot, though, right? He was in the candidate list. You want to try positive 4 next? Positive 4 may have some hope here. 4 times 2 is 8. 8 minus 0 is 8. 8 times 4 is 32. 32 minus 4 is 28. 28 times 4 is at negative 16. Not a chance. It isn't going to work. Bummer. Bummer. So the 4.
Wait, what? Yeah, you did it.
Did I do it wrong?
You erased the bottom.
Oh, that's an 8. I erased too much. There you go. See? You got to make sure you can read your own handwriting. Okay, so that gives us an 8, and 8 minus 8 is 0. This is looking better now. 4 times 0 is 0. That gives us negative 4, and that gives us a negative 16, and that gives us a 0. Oh my gosh, thank goodness y'all caught that. I erased too much of my 8, and I turned it into a 0. Yay, so we found the other root, x equals 4. Do we need to keep trying the 8 and the negative 8?
No.
No, because now we got it down to an x squared. This is 2x squared plus 0x minus 4. There's no x term. And now I set it equal to 0. And now I can solve. I can solve this one by separating. There's no x term, so I can separate. I get 2x squared equals 4. That means x squared equals 4 divided by 2 is 2. And now when I extract the square roots, I can't forget to remember to do what on the right side? Plus or minus the square root of 2. Oh my goodness. These are called irrational conjugate pairs. It's 0 plus the square root of 2 and 0 minus the square root of 2. So if I did want to try out the remaining 8 and negative 8, would they have worked? No, because the last two roots here were not rational. They were irrational. So if I list all 4 of my roots, I get negative 1/2, 4, and then I get the conjugate irrational pair plus or minus the square root of 2. Plus or minus the square root of 2. Conjugate pair. 0 plus the square root of 2, 0 minus the square root of 2. Wow, wasn't that fun? Now, if I wanted to sketch the graph, let's go ahead and sketch the graph. Here's negative 1/2. Here's 4 over here. The square root of 2 is like what? 1 point something? So it's going to be right around here, the square root of 2. And it should be right around over here, the negative square root of 2. Now, because it's a 4th degree polynomial, I know it has the same end behavior. The leading coefficient is positive, so you can do it a little bit more quickly. Does it open up or open down? It opens up, right? So whenever it's an even degree polynomial, you can always think about it opening up or opening down because it's the same end behavior. And if it's positive, it opens up. So both end behaviors are positive. Yes, yes? So it's top in, top out. These are all m whats. What's the multiplicity of all these roots? They're all 1. So it's going to come in like this. It's going to go like that. It's going to do like this. And it's going to look like that. Is this going to be an even function?
No.
Ah, careful. An even function would have to have what type of symmetry? Y-axis symmetry. I drew it to kind of have y-axis symmetry, right? But is that the accurate nature of the graph? Do the numbers tell a symmetrical story? No. If it were to be symmetrical, I would have to have roots at negative 1/2, negative square root of 2, and positive 1/2, positive square root of 2. But I don't. So this is an even degree function, but it's not an even function. Can we find the range of this function? Yeah, no, you're right. Because I don't know the local mins nor the local max. The local max doesn't affect the range, but I don't know what the local mins are. One could be lower than the other. It is going to be bounded. I do know the range is bounded, but without calculus or calculator, we can't find them. And we're going to leave that for another lesson another day. Okay? Right now, I'm interested in you getting this far. So, how did it feel to be a lonely teenager in prehistoric Earth when dinosaurs roamed the Earth and there was nothing to do but sit around at home and try out possible rational roots using synthetic division? We only had 10 of them to try out. How many did we actually end up trying? We tried out 7, didn't we? We never tried out positive 4 or plus or minus 8. But we did 7 of the 10, and we had a good time doing it, didn't we? We did do positive 4. So we actually tried out 8. Yeah. We tried out 8. We just didn't do the last 2. My bad. Y'all right. Okay, so what are we going to do tomorrow? Tomorrow we're going to summarize what we just came up with here, the radical conjugate irrational theorem, okay? And then we are going to finish the notes, I hope, maybe, I'm not going to rush it. We may have to finish the notes on Friday. If we finish the notes on Friday, the worksheet we do on Monday. If we finish the notes tomorrow, the worksheet we do on Friday. Do you think at the pace we're going, we can actually finish tomorrow? I don't think so either. But we'll give it a try. We'll give it a try. No promises. Be working on the worksheet as if it would probably be due on Friday. You don't want that thing to sneak up on you. All right, any comments or questions before we depart from the recording? Was it a good day? It was a good day. We did example, what did we start with? 7? So we did 7, 8, and 9. That's not a bad day. Okay, adios.